Hello, everybody. Thank you for coming to this Cruise Data Science Initiative, the Learning Lab 7. Today, you're going to be working with Dr. Brian Russell. He's your VP of the CGG software, or president. You're the president, right?
No, I'm not the president. I'm VP.
Not yet. Okay.
No, I don't like being president.
Okay. And he's going to be talking today about clustering for seismic phase classification. So, Brian, if you could start sharing your screen.
Sure, I'll do that right now.
Then we're going to start the explanation. All the codes, they are actually available. If you go to the chat now, you might actually see that we upload some links. One that's go for a Google Drive folder where you can download all the files. And then you also include another one for the GitHub as well, where you can download all the files that you need for today. So you can actually watch and run while you are working today.
Okay.
Okay.
So thanks, Marcelo and Daniel, for setting this up. And what I'm going to be talking about today is unsupervised seismic facies classification. Actually, that's a misprint there. I should say FACIES, but that's life. Classification using Python. And the agenda, so I'm putting myself as a guest host. You, of course, the regular hosts are Marcelo and Daniel. And I'm going to, well, there's been a brief introduction we've already had. Then I'm going to go into the theory of unsupervised learning using k-means and Gaussian mixture modeling. Because I think it's very important you don't just link up with the Python or the scikit-learn options. You should really understand what's happening under the hood. Then I've got 3 Python exercises, and I know normally you have them in notebooks. I'm kind of old school. I run a Spider. I just run Spider, so I have 3 different files in Spider, and I've got some files I'm going to be reading off my own Windows hard disk. But I think it's probably more. I think Daniel's already been putting them, and Marcelo has been putting them into kind of notebook format. Is that correct, Daniel or Marcelo?
No, actually, we kept them in as Python.
Okay, you just kept them as Python files. Okay.
But if they need to run it in the Jupyter Lab, they can just open as Python, and then they can run it directly there. If not, they can open in any Python terminal they may have.
Excellent. Okay, and then we're going to run the Python code, and finally, I'll make some conclusions. All right, so let's. Oops, yeah, there we go. So there's an excellent article. I've actually got the references here if you want to download this article. It's quite old now, written in 2003 by my colleague Thierry Collieu, who's still with CGG. And they were the first to apply unsupervised clustering techniques to seismic facies classification. So the left 2 panels here show the use of the self-organizing map, or SOM, or some people call it the Kohonen self-organizing map, with 6 classes and 12 classes. And the right 2 panels show the k-means technique with 6 classes on the top and 12 classes on the bottom. And you can see there's a little difference between those 2. Now, I am not going to talk about the self-organizing map technique today, partially because it's quite different than the 2 techniques I'm talking about. It's a very useful and interesting approach, but also because the SOM technique is not available, as far as I can see, in scikit-learn. There is probably a self-organizing map technique out there that somebody's written in Python, but I haven't seen it, and I'm not using it today. But I recommend looking at the SOM technique if you have a chance, or maybe one day I'll actually put a little talk together on that as well. But I am going to focus on k-means, and I'm also going to talk about a related technique called Gaussian mixture modeling, or GMM, which is another clustering method, and they're quite related, even though they look quite different. Now, recently, much more recent article by Wallet and Hardesty interpretation applied the GMM technique to seismic facies classification also. And here's a picture from their talk. So the 4 panels show the application of GMM to a set of amplitude slices through a seismic volume. So you can see the upper left shows 2 clusters, the upper right shows 3 clusters, the lower right shows 5 clusters, and the lower left shows 5 clusters and the lower right shows 6 clusters. And you can see as you add more clusters, you get a lot more detail. And obviously 2 is probably too little. 6 is starting to get quite interesting. Now it's unsupervised, so you don't necessarily know what the stratigraphy is. You have to compare that with what you think the stratigraphy should be. All right, so that's showing a couple of examples from the literature. Now let's look at the actual theory now. So the k-means algorithm is actually much more simple to understand than the Gaussian mixture model algorithm. Basically, we start with n m-dimensional data points, and where m could be m attributes, m data slices, and so on. And the k-means algorithm divides these points into k clusters. That's where the k comes from. And it's implemented as follows. You pick a number of clusters, you have to tell it the number of clusters, and you would divide the input data points randomly into these k clusters. So each will have to start with approximately n over k points. Then you compute the m-dimensional means of the clusters. You compute the distances between each point and each cluster and assign each point to the cluster for which the distance is a minimum. And the key concept here is distance. What do we mean by distance? And I'll explain that in a second, that there's different interpretations of distance. Then you recompute the means based on the new cluster assignment, and you iterate through the above 3 steps until convergence. So as I said, the key assumption is that we know how many clusters are present. So in a typical application, you may want to try different values of k. There are also some fairly sophisticated algorithms out there that try to figure out for you what are the optimum number of clusters. Here's a very simple example that I created a long time ago. And you can see the red points are the points to be clustered. There's 18 points. And you can see I've created a number of interesting little shapes with them. There's a 3-point shape, a 4-point shape, a 5-point shape, and a 6-point shape. And you can see the blue crosses are the initial means, which you could make them random if you wanted, but these were, because those points are coming in randomly, when it first estimates the means are going to be clustered fairly close to the center of the group, because all those points are random. And this brings up a very interesting point. Our eye immediately sees the clusters, but the computer doesn't see the clusters because the points are coming in randomly. So let's see what happens. The first iteration, the means start moving out. Second iteration, they're better. And by the third iteration, the means have locked on to each of the clusters. And it's done a very nice job. Now I want to say, what do I mean by distance? Well, distance in this case, most k-means algorithm means Euclidean distance or circular distance. So if you draw circles around those means, you can see why it has put those means where you have it. Sees those as 4 different circular clusters. So here's a data set. Again, this was suggested to me by my colleague Chris Ross many years ago. And he said, well, okay, let's try doing an AVO, set of AVO clusters where I've got basically a wet trend, if you're familiar with AVO, and 2 kind of anomalous, basically top and base of gas sands. And much to my surprise, because when I applied this, I was kind of a neophyte at clustering. The clustering was very, very bad. It didn't find those clusters at all. And the reason is it's preserved that circular or Euclidean distance. So my thought at the time was, let's use statistical distance. Now, what I mean by statistical distance is if you look at the Gaussian distribution, which you're probably all familiar with, where in this case, sigma is the covariance matrix, mu are the means. You've got the inverse covariance matrix in there. Well, here's a little more detail. X is in this case, we're in 2 dimensions. X1 and X2 are the 2 dimensions. You work out the means of the two in the 2 dimensions, and you work out the variances, sigma 1 squared and sigma 2 squared, and the covariance, sigma 1, 2. Now, the term after the -1/2 inside the brackets is what's called the Mahalanobis, or statistical distance. Actually, it's a square of the Mahalanobis distance. So it's often written as delta, where delta is x minus mu transpose times the inverse covariance matrix times x minus mu. And of course, if the covariance matrix was equal to the, as I'll show you in a second, was equal to the identity matrix, this results in the Euclidean distance. So statistical distance is simply a more general form of distance, which reduces to Euclidean distance. So let me expand that inverse a little more, and if you invert that matrix, you can see that. And I've simplified it by just writing the terms as A minus B, and C. So this is a symmetric matrix. So using this, let's assume, to make it even simpler, that we'll use 0 mean for the 2 clusters, and use this terms A, B, C. We can expand that Euclidean, the Mahalanobis distance squared, as follows, and you get the term. It's simply an elliptical, basically a rotated ellipse, ax squared minus 2bx 1x2 plus cx squared. So I'm sure you're familiar with this. So if b was 0, of course, it would be it wouldn't be rotated. B is the rotation. So let's look at 3 different special cases. If b is equal to 0 and a equals c, you get the Euclidean distance, just a circular set of points. And so sigma would be equal to basically 1, 1 or 2, 2, 0, 0. If b is equal to 0 and a is not equal to c, you get either a vertical or horizontal elliptical curve. So if a is less than c, you get a vertical ellipse. If a is greater than c, you get a horizontal ellipse. So this one is 0.5 and 2 for the main diagonal. Now, the most complete situation is where b is not equal to 0 and a and c are not equal to each other, in which case you get essentially a tilted ellipse. Okay, so in this case, I've used 1, 2, the inverse covariances 1, 1, 1, 2. Now, this suggested a modification of the k-means algorithm as follows. You pick a number of clusters and divide them randomly into these clusters, just as you do with standard k-means. But then, instead of just computing the means, you compute the covariance matrices within each cluster. And then you compute the Mahalanobis distances instead of the Euclidean distances between each point in the cluster, and assign each point to the cluster for which this distance is a minimum. And then you recompute the means and the covariances based on the new cluster assignments. And you iterate through these 3 steps until convergence. So what I found when I did that, I got a perfect result. So here's the result. In fact, this was back when I was doing my PhD thesis, I thought I'd actually invented a new algorithm, but it turned out it was fairly well known at the time. It just wasn't very well publicized, because most textbooks that talk about k-means just assume that you're using Euclidean distance. Now, although the k-means algorithm can be modified to search based on statistical distance, it appears that most algorithms, as I say, don't have it. So the scikit-learn option, which we'll be using in the lab today, has not implemented this. So a more recent clustering method is called Gaussian mixture modeling, or GMM, and it achieves the same result in a different way. In fact, I've seen the 2 referred to as the hard clustering and the soft clustering approach. So GMM uses what's called the expectation maximization, or EM algorithm, which starts with a random guess of the statistics and then iterates towards a solution. So here's to illustrate it, I've got a very simple example that I extracted from a Gulf Coast data set. Geologically, this is P impedance on the horizontal axis against VP-VS ratio on the vertical axis. And geologically, the set of points in the upper part of the plot represent a shale, the lower points a gas sand, and the rightmost points a carbonate. And these were extracted from a pre-stack inversion of a Gulf Coast data set. Okay, so, and as I said, we're cross-plotting VP-VS ratio against P impedance, which is one of my preferred ways to look to interpret fluid anomalies. Okay, and then these points were actually presented to the algorithm in random order, so it didn't make life too easy for it. So let's look at Gaussian mixture model now, illustrated using that data set. So it's a mixture of n m-dimensional feature vectors, actually, and they're grouped into k classes. So again, it's the same algorithm as we look for k-means. But the difference now is each feature vector has a conditional probability. So you'll see the conditional probability is very similar to my earlier 2D Gaussian distribution, except now the probability of xn given ck is that's our actual probability function. Okay, so we've got multiple covariances now. So GMM starts with an initial guess of the means in the covariance matrices of each class and determines the correct values by iterating to a solution. But unlike k-means, the data is never physically reordered during the process. So let me show you how I started. I basically started with a very simple set of means and covariances. As you can see, the means are 2.25. 2 and 1.75 for each variable, and each of the covariance functions was simply the identity matrix multiplied times a quarter. So that's definitely not the right answer. So that's where EM started. Now the next slide's a little messy with the math, but you may want to look at this in detail later. But the expectation step determines what's called the responsibility for each training point, and in each class using Bayes' theorem. And then the maximization step involves re-estimating the components in the following way. So again, there's a lot of math here, but that's the actual messy mathematics for the algorithm itself. And I'm not going to go through it in detail, but it basically, you first determine the expectation for each training point, then you maximize it by iterating through this. And it's repeated till convergence. And here's the clustered result, a very simple example. And the reason I use this example, each one of those has a kind of different elliptical shape. So the colors can be thought as labels, which tell us how to classify the points. And the final statistics are like this. You can see that, 3 means, obviously, you can read them off. The first covariance matrix is, let's say 2 of them are negative and 1 is positive. So, sorry, and by the way, I thought that was the opposite way, but it's the inverse covariance matrix that we're looking at. So the negatives switch when you work from the forward covariance matrices to the inverse. Okay, so what I'm going to do is I'm now going to switch to Python, use Spider, use Python, and I'm going to use some scikit-learn off-the-shelf algorithms. And I'm going to use 3 examples. I'm going to start with the classic blobs data set. And if you've ever looked at any machine learning book, every one of them uses blobs as a kind of data set to get you started. And as I say here, all the authors seem to shamelessly copy their examples from the scikit-learn tutorials. Now, a more realistic set of 3 elliptical clusters is my second data set. So I actually created that. And actually, I could have created it in Python, but I'm still much more of a, I still find MATLAB really easy to use. So I created them in MATLAB, then saved them to disk. And then finally, up until now, these first 2 are exactly what I've been showing you, just two-dimensional examples where you can visualize it on a 2-dimensional plot. But the real power of these clustering algorithms is when we go into multiple dimensions. So I'm going to do a multidimensional seismic example that we'll see has 5 dimensions. So let me just look at a little more detail. Making blobs. The classic blobs data set, you basically from scikit-learn, you import a little program called make blobs, and it makes a blob with, you tell it the number of samples, you tell it the standard deviation. And for this particular setup, that's what my initial clusters look like. And that's what we're going to see as a starting point. And since there's no covariance term, it's all standard deviations, the blobs will be circular. To create clusters with elliptical shapes, I use the MVN RND, multivariate random option in MATLAB, but actually it turns out there is a multivariate random option in Python. So since this is a Python session today, I probably should have done it in Python, but I was lazy. I already had it written in MATLAB. And then I randomized the order. And in fact, I actually randomized the order in Excel. There's a really simple way to do it in Excel, where you assign a random number to everything and then simply order from smallest to largest. So each cluster had 50 points, and their final forms shown here. And notice for the blobs, there was no overlap. So this is a pretty easy problem for k-means and GMM. But this one is a much more difficult problem because the clusters have shape from the ellipses, and they're also they're overlapping each other. And basically, here's the technique. I used the same covariance matrix for all 3, and you can see I've got 3 means. All right. So in our third example, we're going to apply the k-means and GMM algorithms to the Blackfoot data set from Alberta. So here's the here's one seismic line from the 3D volume. And I'm going to apply it to a 10 millisecond or 5 sample window. I could use a bigger window, but I just decided just to show the example, use a 5 sample window below the lower Manville event. And this means we're actually going to be doing the clustering in 5-dimensional space. So we can't actually visualize the clusters themselves anymore. We can't visualize 5-dimensional space. So we're going to look at the final result and look at what, and these are going to be facies that are produced. Okay, and so oops, somehow sorry, I didn't finish that. I forgot to put the figure there, but anyway, we're going to see the figure very shortly. So. In fact, here it is. Here are the slices. Anyway, let's get out of the PowerPoint, and let me now go to Python. And I've already run something here.
Can I just show them how to open in the Jupyter Lab
Yeah.
first? So okay, I'm gonna just share my screen quite fast in here. So don't worry, you don't need to stop. It's gonna stop automatically.
Yeah.
So if you guys go to the links that you sent on the chat, from the Daniel's link, we have the GitHub, where we have all the files here that you can just download. And you just come here in this green button, code, in the arrow, and you can download the zip file. Or in the other one that I sent is the Google Drive folder that is gonna contain all the same files as well. You just come in here, click the arrow, and do the download as well. So it's going to download everything in a zip file. Brian is going to be showing his an example running in Spider, because if you look here to the files that you are working with today, they are .py. So they are regular Python macros. So they are not notebooks, but that's not a problem. So that's quite easy to run. You can select other editors to run if you don't want to use Spider. The best one that I prefer to use is the VS Code, but here I'm going to show you also how to run in the Jupyter Lab. They're going to be a little hard to run in the Jupyter Notebook, so I suggest you guys to just install the Jupyter Lab. After you launch, you're going to have the Jupyter Lab also in a tab in here, and you just have to go to the folder with all the files that you downloaded. So for each one of the Python files, you can just open in here by double click. So you're gonna open the file that you wanna run. You just do a right click and create console editor. And then you can select which environment you're using. I'm just gonna use the base one. Another thing that I like to do, I like to include here on the side. So everything that you want to run in here, you just go to the row that you want to run. You can see where I am, and you just press Shift Enter, and then you're going to run the row that you're in or the selection. In this case that you have two rows, they are broken, one code broken in two rows. If I just do Shift Enter, you're going to have an error. If you want to run this, you have to select both rows and do the Shift Enter. So it's not, so it's going to run. So here, just importing the libraries and just going to show the first plot by Shift Enter. So everything is going to run and appear here. If you want to now go for the next code, like the Blackfoot one, you also have to create for each code a new console editor. So you can have a console editor for each one of them. So I'm just going to include it here on the side. This is for the blobs and this is for the Blackfoot. And the same way, when I run in here, it's going to run in this editor in here. So that's the easiest way for you to follow those instructions today. So now I'm going to go back to Brian. If you have any questions on how to run this, please just send a message here, and me and Daniel are going to be try to help you.
Great. Okay, thanks. Do I have to share again?
Yeah.
Yeah. Okay. Thanks, Marcelo. I hope you all got that, because I like Daniel. Sorry, like Marcelo says, I'm running in Spider. So basically, actually, let me make it a bit wider. In fact, I think we can make this, but I don't really need the, I don't need the space, but so I talked with Daniel before we started, and he suggested maybe running it step by step, but that's very time consuming. And basically, there's not a lot going on here. Actually, wait a second, I'm in the wrong place. Okay, we're gonna start with clustering blobs clustering, because that's the simplest one to use. So I'll just talk you through what I've done here, and then we'll go ahead and run the, we'll go ahead and run it and see what the results are, and I'll explain how to interpret the results. Well, actually, I want to really explain how to, through this, how to link in with the k-means and GMM algorithms in scikit-learn. So basically, the first thing we're going to do is make blobs. So from scikit-learn datasets, we import this make blobs option. And for my first set of blobs, I'm going to use 150 samples, 4 centers, and we're going to use a standard deviation of 0.5, which is a kind of halfway value. You're going to shuffle the data, put the true, and there's some subtle things in here. You can go and read the documentation. In fact, I added the documentation to my PowerPoint if you're interested in looking at it. But once I make these blobs, I'm going to start, and I'm going to do a scatter plot. Okay, so what's important to note is capital X here is going to be a 2-dimensional vector. So two column vector where X 0. Remember, in Python, unlike MATLAB and Fortran, the first column is 0th column, not the first column, and the second column is the first column. So basically, the X, even though it's capital X, well, it's a bit of bad notation here, because small y doesn't really mean y. So X we could think of as having two, y represents actually the labels here. So capital X has 2 columns let's call it X1, the X1 direction and X2 direction. So capital X colon 0, that means take the points out of the first column, which is the X1 direction. X colon 1 means take the points out of the second column. And I'm going to actually plot the labels as color. So the Y are the labels, okay? So, and then I just say, put the labels on X and Y, and the, actually, I'm using capital X and capital Y as my two directions, or my two coordinates here, and the initial clusters with the color label. All right, so that's gonna be our plot of the initial values. Then we're going to do k-means. So from scikit-learn dot cluster, we're going to import k-means, and we're going to do a very simple just k-means with 4 clusters and default all the other parameters. And you can also, so once you've done that, you have to fit X, so k-means.fit X, that's going to look at the X values and, or attach the X values, and then Y k-means is the prediction, the predicted labels. So Y k-means are the labels themselves. So we're going to scatter, again, we're going to scatter X0 and X1, and we're going to show, for the color, we're going to show the k-means, or the Y k-means. Okay, so that, and again, we're going to label this and plot the color bar. Now, the Gaussian mixture model is a little more complicated. So from scikit mixture, we import Gaussian mixture, and I'm going to call the actual result GMM. And so that's the actual mixture components. So we're going to use 4 components. Covariance type. Now, covariance type's interesting. Full covariance means exactly what I was describing, where you've got a totally arbitrary covariance function. You can use a spherical covariance, so you can use those other simplified covariances if you want. Okay, and then again, Y, GMM are going to be the predicted values. And now the other key thing, oh, I didn't explain this k-means very well, because the Y k-means, I should have made that a little clearer what that is. That's the actual, those are the actual mean values. So we're gonna, so when we're plotting the mean values here in color. Okay, now same thing for GMM. Now instead of calling them the k-means here, just to make life a little difficult, in Gaussian mixture, they're called the centers. So we'll say the G centers, or the GMM means. And you can also look at the covariance functions. So G underscore covariance are the GMM. I'm attaching the covariances to that. Remember, you have to, and I learned this the hard way, you've got to put a little underscore at the end of covariances. You can't just type covariances. And I also want to see the weights. So G weights are the Gaussian mixture weights. And then finally, I'm going to plot this now, and I'm going to print the covariances and also the weights. So let's run the whole thing now that I've gone through it. And you can see here's the result. Here are the initial clusters with the labels. Now, one thing here is going to be a bit confusing is it arbitrarily comes up with the clusters. So the order of the clusters can be different, and therefore the color scheme is different. But I think you can see, even though the color scheme is different, the k-means has done a nice job of finding the clusters, and I'm putting the means as these black dots. So the means look accurate as well. And if you compare that to the Gaussian mixture model, basically you're getting exactly the same means, and well, visually they're the same. I should probably print them out and make sure they're exactly the same, but they look very close. And the covariances, notice they're very close to being, so here are the 4 covariances, and you can see the covariance matrices. You can see the covariance values are very, very small. They're an order of there's, you know, they're 100 times smaller. So they're very close to circular clusters. It's never going to estimate them perfectly as circular clusters. Okay, so as I said, this is a simple problem. Now, one thing I should do, let's make a few changes here. Let's see what happens if I was to make the standard deviation 0.1, a very small standard deviation. Now you can see the blobs are much tighter. So you get a very tight, very small standard deviation. However, on the other hand, if I was to make a very large standard deviation, like close to 1.999, you're actually going to see it's not going to run as well this time because the clusters are now overlapping because of that large standard deviation. And you can see, if you look carefully, I think you can see it's slightly different. The results are slightly different. I'm saying that, but I'm having trouble. Well, yeah, I can see little things like, for instance, there's 2 dots here, whereas it's 3 dots here. So actually it has, the 2 algorithms have performed differently by using a larger standard deviation where there's more overlap. So if you're, in other words, if your blobs have a reasonably low, you know, standard deviation, they're fairly nicely separated. Let's redo it with 0.5. The 2 algorithms are going to perform exactly the same. If, on the other hand, you have a very large standard deviation, so the blobs are overlapping, it's not going to be as good. All right, so let's go now to the elliptical clusters. And this is extremely similar, this algorithm, or sorry, this Python file to my previous one, except that I created something called 3 clusters. They're elliptical clusters. I load the text, so I'm not creating it from scratch. I'm loading it as a text file. I'm getting the X from one and the Y from the other. And incidentally, when I was writing this script, initially I put all 3 columns in the same file, and that worked. In other words, I had the X1, X2, and the labels for the clusters. The only problem with that is it interpreted the clusters as 3-dimensional. And so when it printed out the covariances, I had 3-dimensional covariances. So I had to split them into the actual two-dimensional clusters file and the 1-dimensional text file, or the 1 column of text. Okay, so first plot's going to be the correct ordering of the clusters. Then I did the same thing. From scikit-learn, I imported k-means. I did 3 clusters down instead of 4. And again, I knew there were 3. If I had said 4 or 2, it would have definitely come up with the wrong result. So you have to have a reasonable idea how many clusters you want to do. And so the first plot does the k-means result, and the second one does the GMM. Okay, so let's just run this. Okay, so you can see now I've got a lot of overlap. Now you can see neither algorithm behaves perfectly. Because there's a lot of overlap there in those 3 clusters and a lot of shape to them. So you can see that, for example, look at, again, the colors throw you off a little bit because it's using different colors for the different in the 2 different results. But for example, you look at these 3 points here, k-means thinks they're part of the second cluster, and GMM thinks they're part of the first cluster, probably because you can see kind of circular nature of those clusters for k-means. This GMM cluster, it's seen that as a kind of shape. And actually, that is a little closer to the right result. Neither one of them gets the result perfectly, but the GMM's got it a little better. Okay, so that's basically exactly the same example I showed first, except the clusters were a little more complicated. They had some shape to them. They weren't just circular. And again, the first one was easier to do because this make blobs option is a very easy option to use, and just make yourself a set of, and you can make, by the way, you can use make blobs, I think in more than 2 dimensions, and as many cluster sets as you want. All right, now let's go to the most sophisticated of the 3 Python scripts. And this is the one that does clustering on the Blackfoot. And what I've done is I've actually created the Blackfoot data. Actually, I used the Hampson-Russell GeoView program, which now has a Python ecosystem in it. I actually used that to grab the data and export the slices, or bring in the slices. So if anybody has access to Hampson-Russell's latest release, you can actually do all the data gathering inside of Hampson-Russell. But I knew we weren't going to have that today, so I simply saved this as the Blackfoot data. And if you look at the Blackfoot data, it is actually 5 columns. Each column represents one map. Now, of course, the maps themselves are not column format. They're actually 2-dimensional format. So you'll see I'm going to have to reshape them. It's actually 118 inlines by 81 cross lines. So the first thing I'm going to do is I'm going to extract, so I'm going to load this as a matrix M, pretty unimaginative name, and I'm going to create 5 submatrices. M1 is simply the 0th column, M2 is the 1st column, and so on, down to 5. And each time I'm going to reshape the column into a 119 by 81 inline by cross line map, and I'm going to plot the map. Now, one thing I discovered is that Python uses a different notation for its matrices. So what would normally be plotted as just a straight matrix in a mapping program, for some reason I had to do the transpose of the matrix to get it oriented the correct way. So I did transpose M1, rainbow color scheme, and anyway, so the first 5 sets of commands are simply plotting the data, the 5 data slices. Then what I'm going to do is actually in this case, I think I do Gaussian mixture first and k-means second, but so I'm going to do Gaussian mixture. And notice up until now, we've only been using 2-dimensional data sets. Now we're using 5-dimensional data set, but we don't have to tell it that. It knows that it'll figure out that M has 5 dimensions. The only real thing I need to tell it is how many components or how many clusters I want to do. And I said 10. Well, we'll experiment with some different numbers, but I initially said 10. So we're going to do 10 clusters or 10 components for the Gaussian mixture. And then we're going to reshape. We have to reshape the file to actually plot it. And we're going to show the file. And then same thing for k-means. I import it from scikit-learn. And again, it's an easier, k-means is easier. You just tell it 10 clusters. And then I find the label. By the way, I have to get the labels by doing k-means.fit. And then I also have to reshape the labels because I want to make sure the labels are in map format rather than column format. And I plot that result. Okay. And then, by the way, I've got a couple of save files down here because I wanted to actually look at those labels, but I'm not going to use that today. And I'm also going to print. Now, I'm going to print the weights, but if I print the covariances, I found that it was, maybe I'll reveal those values. I actually grade them out because I wanted to just look at the maps, but maybe we'll look at the covariances in a second. All right, so let's run this script now and see what happens. So the first 5 plots are the actual slices. And it takes some time. And now this is Gaussian mixture modeling with 10 clusters. And there's k-means with 10 clusters. And what I find is that Gaussian mixture modeling tends to be more, give you more reasonable results. You can see some very nice continuous events there, whereas k-means tends to break things up, although it's broken them up, but you can see the major features. By the way, let me just go and look at my PowerPoint for a second. And yeah, this is a little better because I captured all those images. So those are the Blackfoot data map slices. And you can see there's a very strong high amplitude event in the map 1. It's starting to disappear. It's going to get a little more focused, then it almost disappears completely. And also there's a little stratigraphic channel that starts appearing, and it's most clear in the 5th slice. There's also this very large kind of blue blob in the middle here. Now that seems to be a stratigraphic feature that the Gaussian mixture model has focused on or has really found, but the k-means hasn't. So if you look at the next slide, yeah, so here is the colors might be slightly different than yours here, but you can see that big on the Gaussian mixture model, that event has shown as a nice big fat stratigraph, or a big circular or stratigraphic feature, whereas on the k-means it's been broken up. Now maybe it's good. I mean, k-means on the other hand seems to have found that stratigraphic channel through here a little better, although you can see it here in blue. So basically these stratigraphic features are coming through quite nicely, but they're coming through in different ways because, remember, Gaussian mixture has put in some shape to the clusters, whereas k-means is just making them circular. Okay, so let's go back to, go back to this guy. All right, just for fun, let's go in and let's try different amounts. So let's reduce the clusters. That's the fun part once you've written the program, of course, is then you can start playing around with the parameters. So let's go to Gaussian mixture and components. Let's make that 5. And for k-means, let's make it 5. And we'll hit the start button. So here are the 5 slices again. So again, it's dealing with the same data, but now it's putting them into 5 clusters. Oh, yeah, of course I should have changed the heading, but I didn't. So it's still saying 10 clusters, but we know this is 5 clusters. Now what's interesting, even though the colors are different, with 5 clusters, it's much more consistent. Notice that big kind of cluster in the middle to the top middle is the same. So when you go to 5 clusters, it's much more, the results are much more similar. Let's try one more. Let's try, let's try just 2. Let's see what happens with 2. Oops. And by the way, we're almost done in case anybody has to leave. And okay, let's do 2 in there. And be interesting. I don't know if I've even ever tried 2 before. Actually, they are quite different. Again, it's interesting. It's surprising, really. Although it does look like it's shifted the polarity on these 2, but there's definitely more continuity appearing. In this case, more continuity appearing with the k-means than the Gaussian mixture. So it is interesting to see. I mean, let's finish by really going crazy and let's put 20 in instead of. This will be the last one. 20 instead of 10 or 2. And this is probably too many events, but. So there's Gaussian mixture modeling. And yeah, again, you can see they are similar, but again, there's a lot more there's a lot more sort of scatter, I think, on the k-means than the Gaussian mixture model. So anyway, that's it, and I'd be happy to answer any questions. Let me just minimize. Let's stop share here.
Okay, thank you, Brian, for this presentation. I really had fun watching it. It was really nice. I have a couple questions.
Okay.
Have you tried to do a dimensionality reduction just to check the clusters, like principal component analysis? Or
Yeah, that's a good point. That would be something that would be very useful to do. I agree. Yeah, and I think you can do that in scikit-learn. There's a principal components option, right? Yes. Yeah. In fact, you can do the cluster. You can actually use principal components analysis to actually sort those map slices, and so that's what you're saying. Apply apply to the initial map slices, right? To maybe actually create some new map slices where you've taken the information and compressed it maybe into 3 attributes rather than 5, right? Is that? Yeah. Yeah, I haven't tried that, but it's a very good suggestion.
Okay. Let me see. I think we have some questions.
You can probably put the mic on for everybody.
No, we don't. We have someone suggesting to do an introduction to GitHub. Okay.
May I ask a question?
Yes.
Sure.
First of all, I'm really thankful, Brian, for this detailed presentation, and Marcelo and Daniel for preparing this great webinar.
Thanks, Masoud.
Aleki. I am from the University of Campinas in Brazil.
Mm-hmm.
And here, Brian, I met you in person. I had this great honor in the last
Oh, come on.
in London. And as I mentioned to you in the last conference, that you are kind of the mentor for lots of young Jews.
Well, thank you very much, Masoud. You're making me embarrassed, though.
And so my main question is about, I would like to know about your idea about the philosophy of future of the geophysics exploration and artificial intelligence. And as an introduction about my question, because of this situation of the COVID, I participated in various webinars. And in our field, in the seismic data, I have noticed that there is a high focus on the application, such as you mentioned, the SUM, the k-means, random forest. But when I talk with some computing guys, for example, about the SUM, it has been used in the 80s. Yeah. It is not kind of used by the machine learning folks these days.
Yes.
Even the commercial software, OpenDetect for the fault detection is not up to date, or Hampson-Russell, the new DFNN for the machine learning is not kind of up to date. We are not using the new algorithms like, I don't know, such as autoencoder training. There are lots of new algorithms for the classification and for the deep learning algorithms. And as a geoscientist, I feel that we are kind of far behind the advanced algorithms in application of seismic data. What do you think? You think that we are kind of behind the application of seismic and artificial intelligence?
No, I don't think we're behind. I think we're seeing constantly people introducing new methods. I didn't quite. Okay, was one of your questions, how do I compare these methods to the self-organizing map?
Yes.
Yeah, self-organizing map is a nice technique. It is quite different. The reason I didn't include it today, well, as I said, 2 reasons. I didn't have the algorithm readily available, and also it's quite different than k-means and GMM in that it does a dimensionality reduction. It takes the data and projects it into a 2-dimensional space. So you've got, and then actually a lot of companies, getting back to Marcelo's question, actually use dimensionality reduction. They actually use principal components to identify which attributes to use. And then they do, in fact, there's a company in Houston that does this. And then you basically use KSOM or SOM to put everything onto a 2-dimensional grid, and then in the grid, in the two-dimensional grid, you identify clusters. So it's quite a different approach than k-means. K-means works in the same dimensionality as, if you have 5 dimensions, it's going to work in 5 dimensions, whereas k-sum projects everything into 2 dimensions. So that's one, you could argue it's an advantage and also a limitation. So it's quite a different algorithm.
I am also not fan of the sum. In my idea, it's kind of old for our.
Well, it had its day. I mean, it was very popular in the 80s and 90s, but I think it's still a useful technique. I wasn't trying to downplay it today. I just didn't give you an example of it. There's a lot of other clustering techniques. There's some dB scan. In fact, those of you who are with Cruise, I think the majority of the people here today are with Cruise, or a lot of them are. You would have seen a talk a couple of weeks ago where is Matt here? Is Matt on the? I don't see him,
No,
but anyway, Matt Eade gave a nice talk where he used dB scan, and I was actually going to use the dB scan option because I actually applied it a few times, but I didn't get great results. dB scan seems to work best where you have kind of clusters that overlap each other. In fact, there's an option, what's it called? There's another option to make these clusters that overlap. And in that case, if you have a kind of binary situation with they're almost like interlocking, it's called moons, that's it. You can make these half moons that interlock. dB scan will find it perfectly, but k-means and GMM don't. But when you go to higher numbers of clusters, then dB scan falls down. So one of my intentions is to go back and see if I can optimize the dB scan parameters to get something a little more realistic. So the reason I didn't include it today was lack of time, and also I didn't fully understand, what it was doing compared with k-means, and so that might be something you might want to look at for a future lab.
Many thanks, Brian. Here also at Unicam, we are using the autoencoder training. It's not the same as but it provides some promising result for us.
Yeah, autoencoder is a very nice technique as well. Yeah. Are you?
Again, I'm really thankful for this talk, and I hope to see you in more webinars.
Sounds good. Now, thank you for joining. That's great. I guess I should ask Daniel and Marcelo, are you going to be looking at some autoencoder work in the future? Or?
Yeah, we are doing some projects with that with autoencoders in particular for things like generating seismic data and stuff like that.
Okay.
Yeah.
Excellent. All right. Any other questions? Feel free to email me, brian.russell@cgg.com, if you have any questions. It's always it's quite different doing a talk on Zoom because you can't see the people. It's nice when you're in the same room with everybody, making eye contact.
Not read the public, yes. I agree.
How about Bernie? Bernie, you got any questions?
Ooh, that's asking directly to him.
There we go. Yeah, I put you on the spot.
Up, Brian.
Great. Bernie and I go back a long way. When did we first start working together, Bernie?
1987.
1987. It's a long time.
Yeah.
How about Brandon? Brandon, you got any questions? Put everybody on the spot here.
Yeah. Usually he has questions.
Sorry, I don't have any questions today, I'm afraid, Brian. I'm a little bit distracted. I've got a job interview in 45 minutes.
Oh, well, good luck.
I admit my attention's a bit divided, but thank you for the talk.
You're welcome. And
Brandon
was one of my mentees or mentor. I was your mentor, I think, a few years ago.
Cool.
Excellent. So, all right. Well, I won't pick on anybody else. I guess Marie, maybe. I don't know, Marie. Said I wouldn't pick on anybody else.
No, I don't have any question, Brian. But
Okay.
Thanks for the talk. Yeah.
Good.
I think people are still processing what happened. So, yeah.
Good. All right. Well, thanks, everybody. I guess my hour is up.
So if you don't have further questions, I'm going to stop the recording. And I'd like to thank you, everybody, for joining us today. We're going to be announcing the next lab in a few days. So we're going to just check in the dates that we have in the future. So stay tuned. Thank you.
Excellent.
Let me just stop the recording.